Here's an interesting formula that I found out for the purpose of making this video. It's something I didn't know prior to today, making this video, is that the speed of sound through air is dependent on temperature. So let's see what happens now. Let's say temperature of the air happens to be 20 degrees Celsius. Now we need to calculate the speed of air through that, speed of sound through that air that's got a temperature of 20 degrees Celsius. Right, there's an invisible time sign, but then I'll put it there, so you can just put that in the calculator. Temperature is 20. We'll need a calculator for this. Now, that's the one. Right, there's a fraction there, so press the fraction button. 20 degrees Celsius. Speed is equal to meters per second. That means sound will travel 343 meters every second. Now I want to see what happens if I increase the temperature ever so slightly. Let's say the temperature becomes 30 degrees Celsius. So now T is equal to 30. And just substitute that value into the formula. Since I've still got it in my calculator, I can just go back, use a cursor and edit the 20, make it 30 now. See, let's see what effect that has, the temperature has. Now it's gone to, the speed is now meters per second. So it was 343, it's gone to 349. So it looks like by raising the temperature from 20 degrees Celsius to 30 degrees Celsius, the speed of the sound, through air has actually jumped slightly, has gone up slightly. Now just out of interest, I'd like to see how the speed of sound changes with temperature. When the temperature changes, what effect that has on the speed of sound. So what I'm going to do is have temperature T along the x-axis, along the corridor, and the speed along the y-axis up the stairs. So for that, I can use a graphing tool online. If you just look at the screen, right here I'm going to put the formula. S for speed, square root symbols right here, and just make sure you put everything under the square root symbol now. Right, T for temperature. You can call it any letter you want, you can represent it as anything you want, but I'm using T because it's temperature. Right, / on the keyboard for the fraction. Right, you can see there's nothing appearing on the screen, but if you go back, if I just show you the values that I had when it was 20 degrees Celsius, speed was 343. Speed is 343, and you can see 343 is quite high up along the y-axis, quite high up. 343, but here on my y-axis it only goes up to 5. I'm going to modify that slightly. I'll make that go up to 400. Now you can see here, you can see the graph now. What I'll also do is going to modify the x-axis. Here the temperatures, you can see temperature is going from -6 up to 13 degrees Celsius. I'm going to modify that slightly. I'm going to make it go from -300 up to, I don't know, 150 degrees Celsius. Right, there you go. So that graph there represents the formula over here. Now, just out of interest, when it's 0 degrees Celsius, what would the speed of sound? I'll just click that there. When it's 0 degrees Celsius, the speed of sound is 331.3 meters per second. A little bit further up. Let's try something else. Right, when it's 20 degrees Celsius, you can see it's 20 along the corridor, it's 343 meters per second up the stairs. So when it's 20 degrees Celsius, the speed of sound is 343 meters per second. It's what you just saw right here when we did the calculation. When it's 20 degrees Celsius, it's 343 meters per second. Now, from what I found out online, that this formula becomes invalid for very high temperature. So when the air temperature is very high, then that formula kind of breaks down. This is valid for normal range of temperature. We're talking about our atmospheric temperature. For example, atmospheric temperature could be anywhere between -50 degrees Celsius up to 50 degrees Celsius. So in very cold condition, it could be -50 degrees Celsius, and when it's very hot, it could be up to 50 or even 55 degrees Celsius. And that formula is valid for those temperature ranges. Now, you're probably wondering why this graph stops right there. I'm trying to zoom into that place. It stops at -273.15. It would be invalid for -280. Right, I'll explain why. If you look at this formula again, look what happens when temperature is -273.15 degrees. That is very cold. Right? You've got to understand that is very cold. Let's substitute that into our formula. Right, T is that. Use a fraction button first. Right, -273.15. That's absolute zero. That's very, very cold actually. And over 273.15. Right, zero. So when T is -273.15, S is equal to 0. If I choose a number that's less than that, anything less than that, see what happens now. Let's say I choose T as, let's choose a number slightly less than that, -274. Let's see what happens now. So maybe you can understand what's going to happen. What happens when you do square root of negative numbers? Have a think. Let's try -274. Get a maths error. Right, the reason for that is because now the thing under the square root is a negative number, a very small negative number. Any negative number, when you try to square root any negative number, you'll get that maths error. It's not possible. That is why, if you look at the graph again, this graph stops at value of minus 273.15. It does not exist for anything beyond that.